right, so if you're at home, I just showed them on the calculator what a couple of the derivatives were by observation. You can try it. I'll tell you how at the end. I forgot to hit record. So first of all, we're going to do the derivative of some of the trig functions and two of what we call transcendental functions, e to the x and ln x. So I want you to write right here the derivative with respect to x. This, by the way, just gives you the independent variable, what's changing. When we start doing the real world problems, that'll become a t, or sometimes a theta, like for an angle changing, what happens. But we will do of sine x. And I showed them on the calculator that it gave them the cosine wave. So I want you to write that down. The derivative of sine is cosine. The derivative of cosine is negative sine. These need to be memorized, and there's a really easy way to keep them straight and all their signs, like S-I-G-N-S. It goes like this, and I would highly suggest, I even find Calc BC still does it, and on almost every test, they go like this. St. Cloud, negative St. negative Cloud, and it ends the way it begins. Your derivatives go this way. So the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of negative cosine sine. Do you see what it gets everything, so you don't have to rethink them about 1,000 times during the year. You can just write this on the side of your paper. And when we do integration, I'm going to write D for derivatives. When we do integration, it's going to work backwards because they're inverse functions. So it's nice. It gives you all the derivatives. So St. Cloud, St. negative Cloud, and it begins or ends the same way it begins. I told these guys that I'm not going to prove this year, but I will link it on today's page of me doing it. Last year, I did this one in class, and then for ELK time, they got extra credit for doing the cosine. I think I'm still going to give you guys extra credit for doing a flip grid explaining how to do the cosine one. I gave them 2 test points. So if you want to, I do the link for the sine. This one falls out really similarly. Okay, so let's do this. 2 test points. Those are huge, by the way. I'd always take 2 test points for, and it's extra credit. Flip, if you're like, I maxed out already, I don't need to do extra stuff, that's fine. For flip grid, which I'll make next hour, proving, you could probably find a proof of it by Googling, but you have to explain it to me, so make sure you understand it. Proving that one. So I'll link this one there. That'll save us about 10 minutes. So let's start. It says find the derivative of each. I would again, St. Cloud, St. negative Cloud. It ends the same way it begins. And let's start. My y prime would be, hopefully you learned that constant stay put. That's the constant multiple rule. So it would be 2 times the derivative of sine. And what's the derivative of sine? I'm done. Constants stay put. All right, this one has a constant. I'm going to write this one as dy dx. It's really 1/2 times sine x. Constants stay put. And what's the derivative of sine? Cosine. Boy, is that hard, right? Man, did I just blow your mind, Ellie? That's hard stuff. Just kidding. This next one. The derivative of a sum is the sum of the derivatives. So you do these each separately. There's really not much work to show. I guess if I wanted to show it really formally, I'll do this one really formally. Maybe you have a professor that says you've got to show everything. Then you'd go like this. You take the derivative of them each separately. But really, what's the derivative of x? You should know that. What's the derivative of x? 1. Yeah, and you can see it. It's actually the derivative of x. Like it's 1, right? But remember, any linear term, the derivative is its slope. Because the derivative is the slope of a tangent line. And anywhere on the line y equals 5x, the slope is 5. So that makes sense too. But it's really, if you want to think about it, it's 5 dx dx. You can think of it that way too. But this is 1. And what's the derivative of cosine? Negative sine. So this would be 1 minus sine x. Done. Super easy. All right. The derivative of the natural exponential function, e to the x. Okay, so let's write that down. The derivative with respect to x of e to the x. Now, those of you at home, I showed them this on the calculator, and I'll show you guys when they're done. What did we find out that this looked like on the calculator, guys? E to the x. Yeah, it's the only function in the world whose derivative is itself. You can't get it wrong unless you're Frank, right? Otherwise, Frank's the new Fromm. Last year, Derek Fromm, I made fun of him all the time. If you wanna, if I offend you, just let me know. Okay. All right. So this says find the derivative of the following. I'm gonna do this one formally, and then we'll shorten them up. The constant multiple rule says constants come out front. They come out front for limits, derivatives, and integrals. So that's something all year. If you're like, there's a constant, whatever you're doing with it, bring it out front. So this is really 5 times the derivative of e to the x. But what did I tell you the derivative of e to the x is? E to the x. I'm fine with you just going here on your worksheet. Okay, but just know you might have a picky professor who says, you gotta show, I'm actually really picky, but not with this. I'm showing you what it looks like formally, but honestly, we can do these in our head, I think, right? So in this one, I'll call it y prime. What's the derivative of e to the x? E to the x. Boy, Charlie. Woo! Right? Blow your mind. What's the derivative of minus 4x, that linear term? Kalia? Negative 4. Is that all it is? Yes, for now. I mean, they do get harder, but starting off here, that's it. So go to letter C. Take the derivative of, and don't write y equals. I do want you writing dy dx equals. I want you getting used to that. You'll know why. Again, we're not in the application part. We're not having things change over time yet. We just have to learn all the rules. So the beginning of the year is kind of boring, I get it, but the end it gets cool. It might be the rate that the electrical current is changing over time if you're an electrical engineer or something. So derivatives are instantaneous rates of change. We're just dealing with them. Our functions are all boring and don't represent anything in the real world. But they will. All right? So next up, actually what was really cool last year is right in, there's a bug. Did you see that? There's a bug just flew by. Anyway, what? There was a bug. Shut up, Blake. And do your homework. All right. So, what was I saying? Oh, right when COVID hit last year, we were in Calc 2 working with logistics growth functions. We were right like the day before you guys didn't have to come back to school on the following Monday. On that Friday, we were working with fitting data to functions that look like this, that grew really fast, then hit a maximum growth rate, and then tapered off. And that's what we were working on. And it was really cool because that's how COVID, when they were always showing, you know how they say we want to flatten the curve, they wanted to do it before they hit this maximum growth rate, which was where the derivative or the slope of the tangent line is at its greatest. So it's kind of cool that they hit it right, so we were able to apply it right away. What'd you put for your answer, Abe?
Oh. 7.
I went off on a tangent. That was punny. All right, go.
7 e to the x minus sine x.
Did you get it right, Charles?
Yeah.
Isn't that easy? All right, let's move on. All right. The derivative of the natural log. I didn't have you investigate this on your calculator. We did the other ones. Those of you at home, again, I'll take you through those at the end. I'm just going to tell you what it is. If we had graphed this, you guys, and we used our Math 8 to graph it, the derivative of the natural log function, keep in mind what that function looks like. It looks like this. If we had graphed it, it looks like, and I'm going to show you why, it graphs the slopes of the tangent lines. They are very positive over here. Don't you agree? And then they get less and less positive and approach 0. Correct? So the derivative graph would be very, very positive and then approach 0. This right here, maybe you recognize. What function, parent function, makes that graph? It wouldn't be over here because we would have x has to be greater than 0 for you to natural log it. But do you guys know what this is the graph of? We've had it a couple times in here. What's that the graph of? Do you remember, Herb? You can guess. We won't make fun of you. Unless you're afraid. Do you remember, Harrison? Do you guys, anyone remember? Do you remember, Dylan?
I'm Jake.
Jake! Why did I call you Dylan? And you let me do it before, too. Sorry, Jake. Yellow sweatshirt. Yeah, oh, I like it. It's the graph of 1 over x. By the way, the graph of 1 over x squared we call the volcano graph and goes like that. But you should be familiar with those. All right, but it equals 1 over x. So that's not too particularly difficult. So I am going to go and do one like is on your worksheet where I combine all 3 of our new ones. The trig, the e, and the ln x. Okay? So if you're doing your homework today, you're going to write dy dx equals. That's the one thing I am picky about. That you're not just concerned about getting the derivative, but that you use proper notation. But I'll let you go through and do this basically in your head today because it's pretty easy. The constants stay out front. The derivative of ln x is 1 over x. The constant stays out front. Blake, what's the derivative of e to the x?
E to the x.
Done. The constant stays out front. And Jake, what's the derivative of cosine?
Negative sign.
So this becomes plus sine x. I'm okay with you doing that on your homework, but I won't give you full credit if you don't write this. All right? Because also when the variable changes, for example, if it was y equals 4 ln theta minus sine theta, I want you to understand that theta is now the independent variable going in, causing y to change. So you would write dy d theta, but it works the same way. What's the derivative of ln x? 1 over x. What's the derivative of ln theta? 1 over theta. What's the derivative of sine theta? Cosine theta. So when there's a variable change, I want you to note that it's really important for when we get to the word problems because the variables are going to change. And if you're always used to just y's and x's, that causes a problem. All right. So for today, I am going to, I'll cover this. I don't think I put any on the worksheet. I told you I'm trying to cut out stuff that's not on the AP test, but this actually did pop up a couple years ago. So I'm going to cover it, but you'll forget it, and we'll come back to it when we're preparing for the AP test. I'm going to go over here, and I'm going to write, what if we change the base? By the way, what's the base on the natural log function? What's the base? E, yeah. But what if I changed the base and did a common log, like base 10 or base 7 or base 8 or whatever? How would that change? So I want you to write this. Log base b of a. And I'm going to go over here and write like log base 5 of 7, just so you can see what I'm talking about with numbers, because sometimes now the variables mess with our heads, okay? Watch what happens with this. Hopefully you learned, right? I'm going to write equals. I'm going to write equals. I'm going to go back and do a little, think it might be algebra 2. Suppose I say I don't know what it is. Right? You should have learned in pre-calculus that to undo the log, you do b to the x equals a. Does that look familiar from algebra 2? You're all nodding, right? So then what we do is take the natural log of both sides. That's always legal. And we're going to get what you were probably told was called the change of base formula. Do you remember doing that? So what I'll get here, we can bring this out front. That's one of the logarithm rules, is powers come out front. So I have x ln b equals ln a. Ava, are you following me or am I going too fast? So if I solved it for x, do you see how I end up getting ln a over ln b? Ln a over ln b. Did you see how that happened? So you always get ln of this over that. So right here, ln of what? 7 over ln 5. So how is that going to help us? I'll show you. All right, so let's write this a little nicer. So suppose I said log base b could be 7, 6, 5, 4, of x. Are you with me? So x is the variable of change, b is some constant that's the base. So it might be log base 2 of x. All right? It'll be ln of x over ln b. Right? Are you with it? Right? So that's where this is coming from. I hate to just show you things. Like, hopefully in pre-calc you weren't just told, hey, this is a change of base. And you memorized it, because then you forget it. I like to show you where that comes from instead of just plopping it right in front of your face. So watch how the derivative comes about. Okay? And I'm going to go now give you a base. All right? If I were to rewrite that with a change of base, what would it be? ln of the x over ln of the 2. Jake, make sense? So now if I were to take the derivative of, and now you'll be able to do these in your head if you see them working. Okay, so this is what you're going to change any non-base. Like if that was log base 7, it'd be ln x over ln 7. Now watch when I take the derivative. Okay, this guy right here is a number. Right? I don't know what it is, but it's a number on your calculator. There's really a 1 up there. So there's a constant that comes up front. 1 over ln 2 times, right, times the derivative of ln x. What's the derivative of ln x? What did I just say? What is it? 1 over x. Notice what happens. You end up with the natural log of that base in the denominator. Now, watch. Had it been ln x, then right here, this would have been an ln e, because that's what it's base. Do you guys remember what ln e is? You should know. What's ln e? It's 1. Yeah, so it is 1 over x. So watch. I know I went through a lot to get there because I like to show you where things work. But if you're doing log, boom, it's just like the natural log, 1 over x, except what's going to be down in the denominator. Yeah, see how easy, if you see it work, whoever said that, was that you, Blake, or is that you, Jake? Do you see how if you see it working, now you don't have to do all this. But I do like to show you, all right? Otherwise you forget. So what's log base 22 of x? Go ahead. Her.
1 over natural log.
Yeah, and make sure you put that in parentheses because it's a constant, so it doesn't look like you're taking the natural log of 22x. It's the natural log of 22x. And again, had this been ln x, it'd be 1 over x, natural log of e, which is 1. Now, your homework, I think, is almost all natural log. So, just so you know, we are done, I think. How am I doing on shortening these notes? You should say great. Say great, Charles.
Right.
Thank you. Jeez, Charles. All right, those of you at home, I just passed out the worksheet, and I just want to make sure they're clear with what notation I need. I don't need to see every little step, but I do need to see you writing the derivative and the independent variable. All right, so for number 1, pi over 2 is a constant, and what's the derivative of sine? Cosine. Minus, what's the derivative of cosine? Negative sine. I really need only see that one line, but I do want the f prime of theta. If it's y, I want you writing dy dx. If it's f, I want you writing f prime. Does that make sense? The first person to get to number 12, let me know. And I'll start this video up again, and we'll go do 2 of those together. Okay? So the first person in here to get to number 12, raise your hand, and I will video those for the guys at home as well. So I'm going to pause the video and wait about 15 minutes for somebody to get to 12. What do you think, Leah? You're good? I have a key for this too that I'll post if I didn't already. All right, guys at home, somebody got to number 12. So when you get there, you should go too. I am going to just hop on at the bottom here, and we're going to go do 2 of them real slowly in number 12. I did not cover them in the notes because I thought I'd save some time and do a couple for you. Can I just steal yours real quick so I can see which ones I want to do? I think we'll do a letter D. Limit as h is approaching 0 of sine of pi 6 plus h minus a half all over h. And I think while I have his sheet here, we will go do letter G as well. Limit. And if you're at home, I did post the key while they were working too, so if you need to refresh to see that, don't forget. All right, we're going to do 2 of them together. Here you go. It says, find the following using the limit definition of the derivative, which is up above. If you've been practicing, you've done it a lot, and there's 2 forms of it. There's the limit as h approaches 0, and then there's the limit as we approach the specific number. They're very similar. Remember, this one is f of x plus h minus f of x over h. Your goal is to figure out what the function is first. What is f? It's always very obvious because you can see it. You locate the x plus h, and it's basically whatever function it's embedded in. So in this case, my function f was the sine function. Does that make sense? You might want to write that down so you have something to look at. But the original function itself was the sine function. And let's say Kalia was doing this in that, like that flip grid. She would have done sine of x plus h minus sine of x over h and gone through the whole thing, correct? But you don't need to do that anymore. We're just recognizing it. So we also know specifically what the x value is. So this is at a specific spot, right? So this is f of x equals sine x, and we're at x equals pi over 6. That's what you suck out of that. Who's the function? Where am I at on the function? Okay? Remember, this is the notation for the derivative of the function. So really all you need to know is, this is the notation for f prime. So for us, what is the derivative of sine? We just did it. Cosine, all right? But it's not cosine x. That would have been if this had been an x plus h. It's cosine pi over 6. Now you might wonder where that a half is. Well, remember, my f function is sine, and sine of pi 6 is a half. So that's why there's a half there. So you need to know your unit circle and to know what cosine, unit circle never goes away. You need to know exactly what the cosine is of pi 6. And remember the half and the root 3 over 2. Oh, backwards. Root 3 over 2, there's a half in the, I wrote it too quickly. Root 3 over 2, comma, a half. So the answer to this one is root 3 over 2. So you don't have to do the long definition, you have to recognize it. So back to this guy. Again, if you haven't done 2.1 yet, this is all not going to make sense. So that's got to come first. Otherwise, this is way too fast. All right, so let's go look at G. Remember, this is at a specific spot. And remember, we said this is f of x minus f of c over x minus c. So I want you to figure out what's the function. Go ahead and write it down. It's easy. You can see it. It's in your face, right? And you have to write down, well, where am I taking the derivative of? Because this is the derivative of your function at a specific spot. So you need what's the function and what's the spot. Does that make sense? So Jake, who's the function in question up here?
Natural log.
Yes, f of x is the natural log of x. This is a formal definition, alternative of it, if you watch the notes, for the derivative of the natural log of x at x equals what value? 2. Boom. So that's what you need to figure out. What is the derivative of the natural log function? We did that today, right? What is it, guys? 1 over x. And had this been ln x, had it not had that 2 in there, but this is going to, so it's 1 over x at x equals 2. All right, does that make sense? I'm hoping that's enough. I skipped the notes on this because if you've watched the 2.1, this is very similar to what we did in there. So it's just got some new functions with it. All right, keep on working.